Welcome to Calculus. I'm Professor Geist, and we're about to begin Lecture 8 on lHopitals rule.
Everyone who's had some exposure to calculus knows of lHopitals rule. Everyone who knows lHopitals rule loves lHopitals rule. But who understands why lHopitals rule works? By the end of this lesson, you will.
Recall that when faced with a tricky limit, lHopitals rule is a good method. For example, if we look at the limit as x goes to 0 of sine of x over x, or the limit as x goes to 0 of 1 minus cosine of x over x, you probably remember that the way to deal with these is to differentiate the numerator and the denominator. The derivative of sine is cosine. The derivative of x is 1. Taking that limit gives you the correct answer of 1. Likewise, in the second example, the derivatives of the numerator and denominator give sine of x and 1, respectively, leading to an answer of 0. But what does lHopitals rule really say? Well, remember the way that it is applied. You begin with a limit of the form of a quotient, say f of x over g of x. Then you try to evaluate the limit. If that works, then great, you're done. If that doesn't work, then lHopitals rule says to differentiate both the numerator and the denominator. Try to evaluate the limit again. If that works, great, you're done. If not, repeat until it does work. Now, the error that some students make is to begin differentiating as soon as they see a limit that looks like a quotient. That is a bad idea. It will fail in those cases. But the question is, why? Why does it work? Why, if it doesn't work the first time, do you keep trying until it does? Let us use the perspectives that we've worked with so far and tailor expand the terms. If we have the limit as x goes to a of f of x over g of x, then expand both the numerator and the denominator about the input a. Now, in the context of lHopitals rule, let's consider the case where the limit of f is 0 and the limit of g is 0. That means that the 0th order terms both vanish. What do we see? Well, we see that we can factor the quantity x minus a from all remaining terms in the Taylor expansions in both the numerator and the denominator. These cancel. And now, when we try to evaluate at x equals a, we're left with the leading order terms. The constants are really the derivatives evaluated at a. Now, if those two were to vanish, then what would happen? Well, we see that once again we can factor out the quantity x minus a, cancel, and again we see that the leading order terms involve the second derivatives at a. Now you might wonder, what about the 1 over 2 factorial? Since it appears in both the numerator and the denominator, it doesn't matter. What really matters is the derivatives. Let's look at this in an example. Sometimes lHopitals rule is much easier to apply than a Taylor series. For example, if we take the limit as x goes to 0 of tangent of x over arcsine of x, well, I don't know the Taylor series for tangent and arcsine off the top of my head, and it might take a lot of work to figure that out. So let's apply lHopitals rule. If we try to differentiate, well, that's going to take a little bit of recollection. You may or may not remember that the derivative of tangent is the secant squared. You may or may not remember that the derivative of arcsine is 1 minus x squared to the negative 1/2 power. If you don't remember this, don't worry. We'll learn how to compute these in just a few short lessons. But for the moment, let's take it as a given. Using L'Hopital's rule, we get the limit as x goes to 0 of secant squared x over 1 minus x squared to the negative 1/2. Evaluating at 0 and remembering that secant of 0 is 1 gives us our answer of 1. That was simple. Let's look at another example, one for which L'Hopital's rule might not be the way to go. The limit as x goes to 0 of x squared log of cosine of x over sine squared of 3x squared. Whew, I do not want to try to compute the derivative of that. It's possible, but not profitable. However, I recall the Taylor expansions for cosine of x, for log of 1 plus something, and for sine of something. These are all very simple. We've done these before. Now, using the fact that the limit is as x goes to 0, and cosine of x about 0 is 1 minus x squared over 2 plus higher order terms, then substituting in for sine 3x squared and dropping all the higher order terms of sine, and then we have to square that. Ooh, this way is not so easy either. But it's not that bad. We're left with expanding log of 1 minus x squared over 2 plus higher order terms. That is in the form log of 1 plus z. The first term is z itself, in this case, negative 1/2 x squared. We'll forget about the higher order terms. Hopefully they won't matter. In the denominator, when we square 3x squared plus higher order terms, the first term is 9x to the 4th. Whew. And now we see that the leading order terms are of the same degree. We get negative 1/2 x to the 4th plus stuff over 9x to the 4th plus stuff. Factoring out an x to the 4th, canceling, gives us an answer of negative 1/18. Now, not all tricky limits are in the form of 0 over 0. For example, the limit as x goes to 0 of 1 over sine squared x minus 1 over x squared. Evaluating looks like infinity minus infinity. That's not going to work. So let us put this over the common denominator of x squared times sine squared of x. The resulting numerator is x squared minus sine squared of x. And now we can apply L'Hopital's rule, or, in this case, Taylor expansion. If we Taylor expand, well, the only thing we need to worry about is sine squared of x, which is the Taylor series for sine of x, quantity squared. What we really want to do is compute the leading order term. So we're going to have a little bit of algebra to do. When we square x minus x cubed over 3 factorial plus higher order terms, what do we get? The first term is x squared. The second term is 2 times x cubed over 3 factorial. Now, what do we note here? We note that the x squareds cancel. Those second order terms and go away, and we're left with the next term, the fourth order term, as the leading order coefficient. Likewise, in the denominator, we see that the leading order term is simply x to the 4th. Thus, canceling the x to the 4ths gives us leading order coefficients of 1/3 in the numerator and 1 in the denominator. Our answer is 1/3. Likewise, if we consider x times log of x and send x to 0, we're going to have to be a little careful. This is a one-sided limit, sending x to 0 from the right. Then what would this be? Well, x is going to 0. Log of x is going to minus infinity. 0 times minus infinity, that's not going to work. Once again, let us put this over a denominator. In this case, we'll move the x to the denominator and call it 1 over x, so that we have a ratio of two functions. In this case, log of x over x to the minus 1. Now, we're going to apply L'Hopital's rule. I'm a little nervous about Taylor expansions here, because both log of x and 1 over x don't seem to have good Taylor expansions at x equals 0. So, applying L'Hopital's rule gives us what? The derivative of log of x is 1 over x. The derivative of 1 over x is minus 1 over x squared. These simplify to minus x. And taking the limit as x goes to 0 from the right, we see that the answer is 0. Now, L'Hopital's rule can also help in evaluating limits at infinity. Consider the limit as x goes to infinity of log of x over square root of x. It's maybe not apparent what that limit is going to be. Log of x and square root of x both become infinite as x goes to infinity, but at what rate? Is there one that is bigger than the other? Well, let's apply L'Hopital's rule. This gives us the limit as x goes to infinity of what? The derivative of log of x is 1 over x. The derivative of x to the 1/2 is 1/2 x to the minus 1/2. This simplifies to twice x to the minus 1/2. As x goes to infinity, this clearly goes to 0. Well, that's the answer, but what does that really mean? A log of x is going to infinity, square root of x is going to infinity, their ratio is going to 0. What that really means is that the square root of x dominates the log of x. It grows much faster than the logarithm does. While it's true that L'Hopital's rule tends to be helpful in evaluating limits at infinity, it's not universally helpful. Sometimes you have to think. Consider the limit as x goes to infinity of the hyperbolic tangent of x. That is, by definition, the limit of the hyperbolic sine over the hyperbolic cosine. Let's apply L'Hopital's rule. Well, this is easy. What's the derivative of sinh? It's cosh. What's the derivative of cosh? It's sinh. And so we see we get the limit as x goes to infinity of the hyperbolic cotangent of x. I don't know what that is, so let's apply L'Hopital's rule again. The derivative of sinh is cosh, and of cosh is sinh. And unfortunately, we're stuck in a loop, and we'll never get anywhere. But using our collective head, we know the definition for the hyperbolic tangent. What we really care about is the ratio of e to the x minus e to the minus x over e to the x plus e to the minus x. Now let's think about that. Those first terms are big. E to the x gets large very quickly as x goes to infinity, and e to the minus x gets very, very small. Let's ignore it. What would we get? Well, I think you could argue that the limit ought to be 1. How can we make that a little more precise? If we factor out an e to the x, we're left with 1 minus something going to 0 in the numerator and 1 plus something going to 0 in the denominator. Canceling gives us easily this limit. This is a useful way to argue. Consider the limit of x times log of x over log the hyperbolic cosine as x goes to infinity I'm going to let you do the work to apply L'Hopital's rule and see what we get. What we're going to get winds up looking a little complicated. Fortunately, there's a hyperbolic tangent involved, which allows us to use our previous result to say that the numerator is going to infinity while the denominator goes to 1. What I want you to do is think about how that answer of infinity could be obtained in your head without L'Hopital's rule. Consider the hyperbolic cosine of x. That's really e to the x plus something small, up to a constant of 1/2. Now, if we take the natural log of that, that should look something like x. Not exactly, but it should grow linearly. And so I would argue that x times log of x divided by something that grows like x should give us an infinite limit. That's a foreshadowing of what is to come, where we want to have a language for discussing or controlling growth of functions. This is called big O, and it's a beautiful language.
L'Hopital's rule, together with Taylor series, form a wonderful set of tools for evaluating limits. In our next lesson, we'll put these tools to use in studying asymptotics, or growth rates of functions. Along the way, we'll augment our tools with one more device, that of big O.